Welcome back to the lecture number 7. This lecture is by itself the basic analysis. It's the same as the glance which is going on in the last lecture of the same glance. We are almost at the end of the course. So next class is about the basic application and basic advanced analysis and its applications. So the 8th lecture will be starting from next time. It will be a totally new glance. So in the previous lecture, we discussed about the some of the basic tools and the data correction methods. Initially, we were discussed about the some of the data correction methods, radiometric methods, data correction, geometric corrections, and spatial correction. In multiple correction, we discussed in the last lecture. So after that, certain corrections when we applied like geometric, radiometric, and atmospheric corrections, that gives an a path to prepare the data for some of the basic operations. But the basic tools which we discussed, that was the preliminary analysis of the data to prepare the data for more further analysis. Now, this basic analysis is again a pre-processing of the data more for the advanced analysis. And here we will discussing some statistical methods, how we are extracting raw information content. Still, this is the data is not yet fully transformed into the information. We can call them it's the raw information content. So we are transforming them into the more informed decisions for supporting our information. So this lecture is the basic analysis as the start title. So basic analysis means understanding what information exists inside the remote sensing data before applying advanced processing, classification, or AI. So we are looking into the remotely sensed data, which is already a little bit pre-processed or some certain data corrections has been applied. So what is exactly available in the remotely sensed data before we need to apply some advanced classification or AI processing. So it helps us describe the data statistically. So this type of the basic analysis is helping us to describe the data more statistically and prepare for the machine learning and AI operations. Detect useful patterns, and this is really important. We are looking now in a stage of we are now in a stage to look for the patterns, especially for the spatial information regarding textures. For it helps us for the feature extraction. We will discuss everything in detail. Understanding the distribution of pixel values. So this pixel values will helping us to discuss the topic spatial information, spatial continuity, how they are helping in multiple the statistical analysis of a Gauss distribution and in histogram equalization and multiple operations. This pixel values or distribution is helping us for further analysis. Identify spatial structure. That is one of the important idea we are going to take more interest in this one, like how we can identify the spatial structures. It is also again based on the pixel values of the neighborhood, which really makes sense, and prepare the better features of our analysis. So when we are having a better features from the existing data, and on those features we can train the models very well. So the main goal is to decide how to extract useful information from the available data. That is the overall idea of the basic analysis, how we can derive more informed information from the current available sensing data. This lecture is basically divided into three main types of analysis. So it starts from the scalar analysis, okay, and this focus is on a one band or a one value per pixel. We discussed last time about the multispectral or hyperspectral data. So here we are discussing only one band from those multiple bands or one value per pixels. So when the number of pixel values is increasing, so it is becoming like a cabinet. For example, we have taken for the intuitions. So it is examples are panchromatic, thermal, or single bands. So we discussed panchromatic is like it is sensitive to all types of visible lights. So it becomes like a grayscale. Thermal is deducting for the temperature in single band. This is the more focused examples of the scalar analysis. Then we are having a special relationship or special analysis. So they are discussing the relationship between the neighboring pixels. These neighboring pixels is really important. As we discussed that the remote sensing data is mostly in the raster grid form. So we are having the cells which they contain a value starting from the 0 to 255 and the 8 bit, and the bit of the data depends to the power n. We already discussed the bit depth in the previous lectures. So this is really helping us in the texture analysis. In texture analysis helping us in the feature extraction, and this is the semi-wiregram we are designing here. Why the need of some semi-wiregram or semi-variants come into the existence, and what is exactly semi-wiregram, and how we can predict the value which is missing in that one, or which is becoming an as an outlier, or more brighter or lower darker. Kriging is exactly looking for that kind of values or predicting the cell values. So these are the certain examples we will be discussing in multiple data analysis or multiple types of analysis. Then we are having multivariate analysis. This is multi-bands or multiple values per pixels. Now this is exactly making the sense of the intuition. We have taken example of the cabinet with multiple drawers. So in each drawer we are having multiple values. So this multiple values act as a vector now, and they are giving a certain directions in the space now about the multiple spectral or hyperspectral data, where the bands between the where the bandwidth between the multiple bands is very low. So like the band is nanometer, nano of 2 or 5 in the hyperspectral, or if even we are going to ultra spectral, it's much more lower than that. So here we are having multiple bands or multiple values per pixel. So here we are mainly discussing the important concept of principal component analysis or principal component transform. It is one of the main features or example of the multivariate analysis. Like the here examples of givens for the multispectral or hyperspectral or multi-temporal data. Multi-temporal data is simple, like the data has been taken in multiple times. We are starting with the scalar analysis. Then as we through go out the course, so we will see the different types of analysis. Then we will start spatial, then multivariate slowly, step by step. Starting with the scalar data analysis, scalar analysis works with a single band. We discussed already this. Each pixel has only one value. For example, the brightness in panchromatic image. So brightness in panchromatic image is exactly representing by 1 pixel of value. So temperature in the thermal images. So reflection in a one spectral band. So all of these multiple bands represents multiple information. So this is more relevant to single band or per single value per pixels. So this is exactly scalar data analysis means. So reflection in one spectral band. So if you are looking to in a certain band, the reflection, so this is exactly called a scalar data analysis. The aim is to understand the distribution of pixel values. This is the main idea, how the pixel values are distributed across the whole image or the data set. The first example, we are starting of the scalar data analysis, that is the histogram. So histogram is nothing, it shows the how often each pixel values appears in an image. And that is the overall idea of the histogram. And it helps us that almost pixels are dark or bright. As we discussed before this, like in the single or the in the scalar data analysis, the brighter in panchromatic images, this is exactly the brightness or darkness we are discussing. And the overall goal is that to understand the distribution of pixel values. So here the histogram is exactly looking for the are most pixels dark or bright? Are there separate groups or classes? Like if we using the binning process, it is like classes or groups exactly in the histogram. Is the image dominated by one length cover type? I mean, the whole image, we can look at it, it is dominated by a certain length cover type. Our different surfaces are separable. So if we look into the data, it is an average image and there is no much more bright and dark. So we can look into the length cover objects more clearly, and it is separable or it is visible. All these question asked is really important in the histogram based on the value distribution or the pixel values distribution we are understanding about, and we can correct them and we can manage them and we can control. For example, in a near infrared band, water may appear very dark, and that's obvious because vegetation may appear bright. In a soil or urban areas may appear in between. That is exactly, or you can also take an of a build-up area that can also be looking in between of the vegetation and the near infrared radar, like as in the water they are absorbing. So the histogram will show you the distribution of the pixel values from which you can understand that how the values are distributed across the image or the data set. Modes. Modes is a peak in the histogram. In remote sensing, a mode may represent a land cover class. So mode is in a part you can consider in the histogram. It is exactly representing a land cover class or one class. Like as we said, if you're using the binning concepts or the grouping or classes in the histogram, so we are exactly looking into the certain group or class. So they are representing one of the peak in the histogram. That is exactly the modes mean. For example, one peak may be correspond to water, like in the histogram equalization, or if you call the histogram. So they are looking into the, let's suppose, water. Okay, in the water they will be showing a one peak. In the another vegetation may represent a different peak. In another build-up areas like or bare soil will be different. These are the classes exactly it can be shown in the form of the modes that is exactly represented. Maybe we can see some of the image example from here. In this picture it is given, like if you see the mode 1, mode 2, so mode 1 is exactly representing and its peak at a digital number is 35. So dn is digital number. We discussed that how we are transforming the continuous into the digital number or discrete numbers. So the mode number 2 is exactly vegetation, it's from the land. Okay, so they are showing the digital number 8. So the third one is valley. Value is optimal thresholding region, so it is very low. So this is how histogram is representing multiple modes in the histogram, and it's you can consume a simple peaks and it represents a certain class. But this is not always the perfect because the different length covers can overlap in pixel values. So especially in the remote sensing, modes may not be all the time very efficient because the length covers can overlap in pixel values. As we will be discussing further the spatial analysis and spatial continuity, we will see that how they are overlapping each other. Now the Gaussian distribution. Gaussian distribution is the class bill, like classic bill shape curve. So in remote sensing, one length cover class is often approximated by a Gaussian curve. So in remote sensing, like a land cover classes is approximately represented by the Gaussian curve. For example, a pixel belonging to forest may cluster around an average reflectance value with some variation around it. This is a really good example. Okay, forest is not a small area, so it is somehow a good enough amount of area where we will see the reflectance as an average because this is overall area's vegetation and it can be really easily reflected. So with some variation around it. So there's some variation around it means like around that forest we can see like bare soil, we can see water, roads, buildings, commercial areas, and more different residential blocks. So these is represented exactly the variation around it. So this is useful because a Gaussian can be described mainly by the average value and the spread around that average. So this is what we are doing to represent the Gaussian. It can be taken the average values and the spread around that average. So let's suppose again the forest example, the around area of that forest, the nearby area, which is for near to the forest, which has some variations. So we are taking the average of the within the forest to become the Gaussian distribution. But in real remote sensing data is often more complex than the perfect Gaussian. So this is exactly we are discussing the Gaussian fitting. We are trying to use the Gaussian fitting, trying to match a Gaussian curve to a real histogram. So we are trying to exactly do this with the real histogram because real histogram is discussing the distribution of pixels. It is useful for identifying classes. Exactly, they are helping in classes like where at different classes like forest, residential block, commercial areas, roads, buildings are located. But it may be difficult because still it has some difficulties to match the Gaussian curve to the real histogram because classes can overlap, and we it's really quite common. In this example we can see in the right side, so certain classes can overlap each other, so matching the Gaussian fitting to real histogram or Gaussian curve is still difficult due to some of the reasons it is given, like difficulties is the classes overlap, pixel may be mixed. So the nearby pixel can also be mixed because it's really highly chances there because of the near neighboring pixel values due to the special feature or characteristic or the spatial continuity. So it is possible sensor noise exists. That's one of the major existing pre-existence issue, and the atmospheric effect may shift the values. So that is another reason possible, and lens cover types are not perfectly uniform. That's for sure and obvious, and it's all the time non-uniform. So Gaussian fitting is useful, but it's not always accurate. Although histogram equalization is one of the important basic analysis we should take into the account within the modes. We are having some basic statistical methods like mean and variance. So mean and variance are the most basic statistics. A mean tells the average pixel values. Example, if a vegetation pixel have a high mean in a near infrared, that means the vegetation reflects strongly at that band. That is obvious the mean of the near infrared we have taken. And there is a possibility in the near infrared, as we have discussed, that the red can reflect very highly green due to the leaf structure. So in this case, for reducing or taking the mean can properly visible show the vegetation with the help of this mean. Variance tells how spread out the pixel values are. So variance is exactly discussing, like as from the word is clear and obvious variance. So we are finding the difference and they are looking how the pixels are distributed or spread out. So example, a forest class with a forest class. This is exactly now we're discussing a single class with low variance is spectrally homogeneous. It's obvious because there is all of the surrounding part of the forest is exactly vegetation. So a build-up area may have a high variance. Why build-up area have a high variance? Because of the saturations in the different things like the construction will be in the middle, so they cannot properly differentiate between the bare soil and the construction in the middle and some sort of the grass over there, roads. So there is a high variance chances in a build-up area. uh, it contains like roofs, roads, shadows, and different materials. So this is exactly what variance is looking for. Skewness describe whether the distribution is symmetrically or shifted to one side. So this is exactly really important in the remote sensing data. Maybe data skewed due to shadows or clouds, mixed pixels, or bright objects. So we are also looking in the basic analysis the skewness of the pixels, and it's really important. Either it's shifted to one side or other side, or it's shifted symmetrically from both sides. And the reason is pretty simple. If it's skewed, could be the shadows, clouds, mixed pixels, or the bright objects. Radar amplitudes data is open right skewed. It's obvious because they can penetrate easily the clouds. So conceptually, skewness tell us whether extreme values are more common on one side of the distribution. This is you can consider like detection of outlier. So they say there is an extreme value and that is causing exactly to the skewness of the data to the one side. This is another important concept of called cortices. So cortices is exactly describing how sharp or flat a distribution is compared with a normal distribution. One, we have a normal distribution. In another, we are looking for the cortex is exactly looking for the flat distribution compared with the or sharp distribution compared to the normal distribution. What do you high cortex is exactly representing? In the right side, we can see its formula and the shape, okay? And we can see the multiple positive cortices and the negative and normal cortices or distribution. So high cortices means the sharp peak and more extreme values. So there is high values in that is exactly causing the skewness also. And the sensitivity to outliers, yeah, it is really sensitive to outliers. There is a possibility it is available. And what do you mean by the low cortices? Means the flatter distribution. So we are having an average values of the pixels, so it will be flat more. Like if you see the negative cortices exactly, or you can assume normal distribution. So values are more spread out, and the values are representing more spreading. And remote sensing cortices can indicate whether a class is very compact or affected by unusual pixel values. This is exactly looking for this kind of distribution of the data. And this is why it's also causing the skewness in the data. Like for the compactness, for the compact or the affected by the unusual pixel value. Like one maximum value in the overall can affect is from the numbers we know about this. So this is we are looking mainly for the sharp or flat distribution with the normal, and what high represents it as a sharp peak or low represents the flatter distribution. And it's mainly caused the higher peaks by the unusual values of the pixels. Now this is the core and important concepts of this lecture. It is a spatial analysis. Spatial analysis, if we go back to the analysis, here we almost, I think so, completed the scalar analysis. So this is exactly, we are now starting the spatial analysis, which is the relationship between the neighboring pixels. So far we were discussing a single, but now we are discussing the neighboring pixels along the single pixel values or the single band. But here, if you see neighboring values in the single band or complete image or data set. So spatial analysis studies the relationship among the pixels, not only their own individual values. The key idea is nearby pixels usually have a similar properties. Why we are discussing that there is a high probability that the nearby pixel usually have the similar properties. As we discussed, like in the forest example again, the forest example in the near infrared in the red, they will reflect a very high vegetation. So in that case, in a certain point of the forest, so its surrounding areas will definitely having more or less the same values. So that's why spatial analysis is one of the core analysis in the aspect of the remote sensing. This is called spatial continuity. The reason this is one important concept we will further explore. For example, nearby forest exam pixels tends to have a similar values. See, again, example repeating nearby water pixels tend to be similar as water absorbs the signals or electromagnetic waves. So there is a high possibility that it can be looking very dark. Urban pixels may show the repeated patterns of a roof or of a roofs or roads and shadows. So this is exactly what spatial analysis means, and it's discussing neighboring pixel values. We discuss spatial continuity means like the Earth's surface properties usually change gradually. This is the good idea. Like we know that the data we are saving is in a raster grid form, and the remote sensing data is not discrete, it is a continuous. When we are looking into the changes, it is gradually, it's not randomly or suddenly or abruptly. So the spatial continuity exacts the reason that there is a similar properties by or similar values by the nearby pixels. So that's why neighborhood continuity, neighborhood pixels become really make sense in this basic analysis of spatial continuity or spatial analysis come into the existence, and it has an importance. So spatial continuity helps connects these two ideas. The real scene is continuous, as we discussed that the acquisitions are continuous, but the satellite image is made of pixels. So this is the transformed or the quantized pictures, but neighboring pixels are related in this case exactly. So we are going from the continuous to this discrete or quantized, but in the quantized now we are looking at neighboring pixels which are related to each other in a single band or in a single image. This is why spatial analysis is important, and this is the reason we are discussing. Now we are looking into the spatial covariance. Spatial covariance is exactly means how similar pixel values are at the certain distance in direction. Here, one important thing is now increases direction because it's number of pixels. So so far it was a 1 pixel, so along the distance. So now we are discussing the direction also. If we are having a distance, so direction is obvious in existence. Conceptually, high covariance means nearby pixel value behaves similarly. If there is a high covariance, as from the word, it's very obvious. Covariance. Variance is a difference, and a covariance. So we are looking to between the two pixel values, neighboring pixel values. So if the variance is high, so it is confirmed that there is a high similarity between the pixels. But if it is a low covariance, means they are less related. Or here we can understand we should differentiate them. Negative covariance means values tend to change in the opposite ways. Like you can say one of the value is going in the increasing way, and the other way is pixel values are coming in the certain distance or direction in the decreasing way. So this is tend to be negative covariance. It helps describe the spatial dependencies. So it is exactly helping us to show us the spatial dependencies. And what is exactly spatial dependencies, we'll see more further. Now, another important concept or analysis in the spatial analysis or the neighboring pixel value analysis is a semivariance. Why here we are first of all discussing the reason it needs come into the existence. So far we have seen in the spatial covariance, we are discussing two different pixel values. Either they are highly covariated or low covariated. And the low covariated we discuss it is more in the opposite direction, you can say. That is exactly so in the negative covariance. In the low covariance means the values are not relevant or similar to each other. In the high covariance, there the pixel values are near to each other. So in the semivariance need, remote sensing data or images is often do not have a constant mean everywhere. As like we are taking in the covariance as an example of the mean, like step by step the pixels or neighboring pixels we are looking into, and as an average we are taking and increasing and looking into that. But semivariance is like it's not all the time covariance is constant. So our the remote sensing images do not have a constant mean everywhere. For example, one part of the imagery may be urban in a single image, but another may be forest and the another may be agricultural land. Because of this, comparing everything to one global mean is not always reliable. And certain examples, if we know there is no more variance in the pictures or not having lot of what we can say in terms of multiple land covers, if you have taken the acquisitions in the residential blocks, so it is obvious we will have a certain things like buildings, roads, and this kind of stuff. So there is a possible we can take a constant mean based on a certain objects in the line cover. But as we have seen an example, if it is not reliable all the time to have the global meaning, so semivariance is solving this by focusing on difference between the pixels pairs. Now we are taking a pixel pairs and we are taking its differentiation instead of comparing all pixels to one global mean. That is the overall idea. So far, we were taking one of the global mean and we were comparing and taking its covariance, as we have seen in the previous spatial covariance. But here, no more one global mean. The idea is we are taking the difference between the pixel pairs. Now, exactly, let's discuss that was the need, how it comes into the existence. Semivariance is measure how different two pixels are as a distance increase. Exactly. We have seen that in the spatial covariance, there was a concept introduced the distance in directions because it's neighboring. So if you're moving from one pixels to the another pixel, so you means you are going in certain direction or a certain distance. So as the distance is improving or increasing, so definitely that is your direction also. So this is the semivariance measures how difference to pixels or how pairs of pixels are as a distance increase. Conceptually, nearby pixels should have a small distance. So if we say the nearby pixels to let's suppose in the forest we have taken from a single image 2 pixel values randomly from somewhere else, they should have a small differences or semivariance, but the distance pixels usually have a larger difference. Why? Because as the distance is increasing, means there is a chances we having a multiple pixel values. So the multiple pixel values can change the variance between the pixels in two or more. So when distance becomes larger enough, pixels become unrelated. And that's exactly what we are looking into, because that's why one global mean is not an ideal in all the case. And this is the basis of the semivirogram. So from here, initially we discussed the need, then semivariance. Now, based on these things, we are drafting or creating the semivirogram graph. Semivirogram is nothing as a graph of the semivariance. We are making a graph where we are locating the exact data. A semivirogram is a graph showing how pixels difference increase with the distance. Exactly, we are discussing these things. So far we discussed it is a differentiating between the 2 pixels, and one global ID is not enough, but we discussed the distance. We are going by neighbors pixels, so neighbor big going by neighbor pixels, so it means we are increasing the distance. So increasing the distance means automatically direction. Let's suppose we are going towards a certain distance directions, so it means we are increasing the distance. So how these semivarograms are helping us understanding the spatial structure? It answer how far does the spatial similarity continues. It shows in the whole picture or the band that tell where the spatial similarity is available. At what distance do pixels stop being related? Where is exactly the spatial relativity or the spatial continuity is stopping anymore? First of all, they are showing till where it is. Then the next thing they are showing where it is stopping exactly. In also showing you is the image is noisy. If in case it is noisy, like uncorrelated more or unrelated more, so this will be reflected in semivirogram. What is the average size of a spatial objects? So each object we are looking at the spatial average size of the spatial objects. So in this semivirograms, we are looking into some of the concepts of a cell range and nugget. Nugget is a small jump. Range is exactly discussing till where the semivariance or semi-variance is available in the data. And cell is exactly discussing the maximum peak of the semi-variance or the spatial variance of exactly two different pixels we are differentiating. So now we will discussing this nugget range and cell step by step. Let's come into the range. As from the word range, it's pretty obvious. Range is the distance between or the distance where spatial dependence in. I mean, now special dependence in at cell is starting. Cell is the peak exactly. Before the range, pixels are spatially related, and one pixel gives information about nearby pixels. After the range, pixels are mostly independent. It is changes, its value is uncorrelated anymore. Knowing one pixel does not help much to predict the other. After the range, if we are looking to predict, we will discussing one topic of kriging, and kriging exactly is looking on predicting the next value. So how we should know where we should predict anymore the missing values or the noisy data or smooth the data, it is exactly from after the range. It is exactly helping us that here data is or the object is more uncorrelated due to this spatial continuity because it ends here. In Earth observation, the range may correspond to the average size of objects, such as the fields, forest, patches, or urban block. So this is exactly the average size of objects. And why it is an object average? maybe there is a possibility in a single objects we can have a multiple reflectance value. So in a single area where we are looking into the ranges showing the spatial covariance or the pixels are related to each other. So based on that region, we are taking it's an average of the objects like we said fields, forest pitches, or urban blocks. Now exactly cell, as I said from this diagram, we can clearly again say this is exactly cell C0 plus C1. So this is showing as the cell is the maximum level of variation reached by the semivariogram. What do you mean by the maximum reached? Conceptually, it represents the total variation in the data set. Yeah, this cell is also really reflecting the overall maximum difference of the pixel values are also represented. So once the semivariogram reaches the cell, increasing distance does not any much difference because pixels are already unrelated. It means like once we are hitting the cell point, we understood from here the data is uh, represented already its variation at this point. And if we are going to increase the distance more, like going to next pixel values, it does not really much differentiate because already the hit is touched. So maybe the other values which we are looking for may be falling down or the pixel values. So that is any more maybe unrelated because it is once touched. So it means that is the peak point for you. This is the data is not more irrelevant here. And this is how we are representing in the diagram. Last nugget is important. Nugget is it is a small jump in here at the beginning of the semivariogram, and it represents the variation that exists in even at every short distance. And the reason of the nugget is caused by the sensor noise. The main possibility and atmospheric distortion is still available, and subpixel heterogeneity and max pixels. Objects smaller than the spatial resolution. We already seen that it's slower means that there is a high distortion or high noise. So a high negative usually means the image is noisy or the sensor resolution is not fine enough to capture the real spatial structure. We have seen multiple types of analysis if we see like starting from the data correction, basic analysis, basic tools. Now the statistically uh, methods are more helping us. The data is refining slowly. This is exactly we were discussing the remote sensing in intelligent sensing. So the remote sensing part is already completed before the fifth lecture, and the sixth, seven, and eight is nine is exactly focusing how we should refine the data more for the advanced classification, machine learning, and analysis. We were discussing the nuggets. Nuggets is exactly looking at the C1 point, and this C1 point is causing exactly the small jump, and it could be multiple reasons we discussed in this slide. It could be the sensor noise, atmospheric effect, or disturbance, or the subpixel heterogeneity. Subpixel heterogeneity means that the next pixel after that is a different value. So that's why it has a small jump, but the nugget high jump is exactly looking the image is noisy or at the sensor is not um, enough to capture the spatial structure properly. I mean the resolution is low. Now we are discussing co-occurrence matrix. So as from the word is pretty obvious, co-occurrence. Co mean two and occurrence happening into two in its matrix. A co-occurrence matrix studies how often pairs of pixel values appear together at the certain distance. As we are discussing the semi-variance or semi-variogram, we have seen we are looking for the two pixels difference, not a global ideal mean, or in this case, the same is happening. We having pairs of pixel values appear together at a certain distance. This is exactly like a different form of the single value, single pixels distribution we are looking through the histogram. But in the co-occurrence matrix, we are looking to the pairs of pixel values appear together at a certain distance. because it's a peer, so we will be definitely following certain path or distance, as we will have a direction also. So exactly the covariance is discussing these co-occurrence, discuss the exactly happening of these multiple or the pairs of pixel values at the certain distance. So it is useful for the texture analysis. Exactly, we will be discussing texture analysis furthermore. Instead of in texture analysis, exactly the spatial information or spatial analysis we have seen in the previous lectures. So one of the texture country attributes we have seen in the spatial information. Instead of only asking what value does the pixel have, like a single value, it asks what value does the pixel have compared with its neighbor. Within its neighbor, they are looking into the value now. This is help describe patterns such as the smoothness, roughness, repetition, contrast, in a homogeneity. And in the next slide is discussing about the gray level co-occurrence matrix. We discussed the co-occurrence matrix. So gray level is exactly the practical application of the co-occurrence matrix. So GLCM means a gray level co-occurrence matrix. It is the practical version of the co-occurrence matrix, like when we are applying in the computer or in real time. It uses moving the window across the image. So we are having a certain kernel, we also call them window, across the image and counts how often pixel values combination occurs. This is exactly GLCM is discussing. GLCM is important for extracting texture features. We have seen in the co-occurrence matrix, it is useful for the texture analysis. So we are extracting using by degree level co-occurrence matrix. So this is the practical application of the co-occurrence matrix. We have seen semi-variogram. Okay, we have discussed in the spatial analysis, what is spatial analysis, what is spatial continuity, what is the need of the semivariance. We discussed the semivariance, we discussed the semi-variogram, we discussed the co-occurrence matrix and its practical application of a GLCM. Now we are discussing some of the texture features. Okay, what is texture features and its meaning? Energy, measure the homogeneity or uniformity. And the contrast is looking for the measure local differences. This is exactly what we are doing in the texture features. And the correlation measures relationship between the neighboring values or the neighboring pixels. It is really important because based on this correlation, if we understand, we are changing its contrast, like measuring the local differences and also even measuring the homogeneity or uniformity, because we understand that the data is homogeneous or heterogeneous or the pixel values. Variance measures spread of gray levels. This is we already discussed, and it's helping by measuring this spread of gray levels, and we have seen it's helping exactly by the co-occurrence matrix or covariance matrix. We will look into that also, which is exactly looking to compare the two pairs of pixel values, and we know how to extract based on this the texture features. So this is texture features. Now this is important concept. Kriging. The kriging is a special production method. If you take an example for the interventions in the MS Excel, when we are having certain missing data, so we have a type of use and flush. So it's a built-in feature. So flush, when you press them in a certain column and row, you can build up its next value. So what they're exactly doing, they are taking their value based on one of the method, it is by its neighbor. So exactly we are doing the kriging is the same, and the remote sensing, it's estimate the value of unknown pixel or location using the nearby known values. And this is happening exactly in this Excel. Flush option, flush up, flush down, flush right, flush left, and it is based on the special continuity. Exactly, we discussed the special continuity is really important, and we know they have a similar properties used for the peeling missing values, reconstruction of the damaged data, interpolation, the correcting bad pixels. Let's suppose the pixel is more bright or low, dark, supporting geometric corrections in resampling. And conceptually, if a nearby pixels are similar, we can use them to estimate the missing value. That is importantly. Let's suppose we are going in a certain distance, definitely having certain direction also. So we can look into the values. if the values are repeating. So if there is a certain pixel missing or it is abruptly disturbed, so we are looking for filling that missing value, so we can use them. Or either the image is very dark or blue due to that one point, so we can also fill up with that next value. So this is exactly kriging is do. Now this is the third analysis we are discussing. It is really important. Multivariate analysis. So far, it was a single value pixels or a single band. Then it was neighboring pixels, spatial analysis. And the spatial analysis, we discussed multiple things: spatial analysis, spatial continuity, semivariance, semivariogram. And then we discussed the co-occurrence matrix and the practical application of the co-occurrence matrix like GLCM. And at the end, we discuss how we can fill the missing value by kriging. Now, multivariate analysis is the analysis works with the multiple bands at the same time. And based on these concepts, we will be introducing at the end one of the example of the multivariate analysis is the PCT, principal component transforms, or PCA, principal component analysis. Multivariate analysis works with the multiple bands at the same time. This is the important point we should have to take into account. The multiple spectral and hyperspectral data, a pixel is not just one value, it is a vector. So if it becomes a vector for the intuition, we can give them an example of the cabinet of when having multiple drawers. So in each drawer, we have a multiple values, which is exactly a vector. So example of pixel value like blue, green, red in near infrared or short wave infrared. So each pixel becomes a point in a multi-dimensional spectral space. Each pixel becomes a point in a multispectral dimension in a multi-dimensional spectral space. So this is a point now in a space. In a single point, we can say it is also vector in a space. This helps identify the materials because the different surface have a different spectral signatures. This is really important. It is helping us to identify the materials as we know the different surfaces have a different spectral signatures or responses. So now let's see its further analysis of the multivariate analysis. The first thing we are discussing scattergrams or scatter plots. Both of them are similar, different names. It is the gram or plot. Okay, the scattergrams are likely histogram for the two bands. Exactly what we have seen in the single value histogram, and they are discussing how the distribution is happened, and it's looking for the smoothness and multiple operations with the help of that. The scattergram and the scatter plots exactly they are having the show to the pixel values in the one band, but here it is not. It's a little bit different from the histogram. Here over there we were having a values and its distribution, but here we have a two bands. So definitely we are looking into the multiple pixels. They show how pixel values in a one band relate to value in another band. This is exactly how the scattergram is representing. Like in the x-axis, we have a red band. In the y-axis, we have a near infrared band. In the vegetation may form one cluster. Why? Because water may form another cluster. Build up area may form another cluster because they are different. So there, this is the different spectral responses from the land. So scatter plots helps to visualize the separability between the classes. And this is the really core concept, how it's more working same like the histogram. They are showing the different the distributions of the multiple pixels to match their multiple bands for the multiple classes. Multivariate mean. It is again the same mean, but more for multiple bands. In a multivariate data, the mean is not a one number, it is a vector because we are having multiple bands like blue, like green, red. And for each band, we are taking its own mean. Then collectively we are taking its mean, so this is called multivariate band, so it's becoming a vector, not anymore a single number. So each band has its own mean. This is and this gives us the average spectral behavior of a class or a data set. That's why in the multi variate analysis. Multi-mean is also really helping, but it's still not ideal for all the cases. That's why we are discussing covariance matrix. If you see in the spatial analysis, we were discussing co-occurrence. We were discussing two to compare them pixels, but here is covariance matrix. It is this more or less the same, but it is a little bit different. The covariance matrix describes how bands vary together. So it is discussing on the bands level now. Over there, we were discussing based on the pixel values of 2 pixel values in its happening or looking into the value over the certain distance and direction. Here we are passing from one band into the another band and then looking into the covariance. This is describing how bands are together. It tells us which band increasing together, which band decreases together, which bands are independent. Independent means they are not anymore related. Which band carries similar information. Exactly. Diagonal values represent variance of each band, and off diagonal value represents the covariance between the bands. So this is exactly the covariance meaning is now we have multiple bands and they are showing us the information across the multiple bands. Either it is increasing, decreasing, the information is similar or it is independent, and the diagonals are representing the variance of each band, because on the diagonal and the covariance of a diagonal matrix we are exactly having the variance of each band. So each band is separately different from the another, but the off diagonal representing the covariance between the bands. So covariance, as the word is exactly reflecting the same. Covariance. So covariance, if you see in the off diagonal values, so they have a common variance between the bands. If they don't have, means that's obviously on the diagonal. So the diagonal is representing the difference, and there is no covariance. There is no common variance between the bands. It's pretty simple concepts to understand in terms of the basic analysis, and I'm trying more in terms of the formulation, all this stuff to understand the concepts. Now the correlation matrix or the covariance matrix is you can consider this is the standardized method, like as we have seen in the co-occurrence matrix is the GLCM is the practical method which we are implementing, and it is the same in the correlation matrix. For example, I would like to show again. If we see this is the co-occurrence matrix, we were discussing how two pairs of pixels values appear together at a certain distance. Then we have seen GLCM is the co-occurrence matrix, and it's the practical version of that. So it is using the moving window or the kernel we discuss and across the image or data set and count how often a pixel values combination occurs. So this is exactly helping us in the feature extraction. So the same is happening here. The covariance matrix is exactly uh, a practical application of that one is the correlation matrix. So this is they are standardizing the covariance into the different values like -1 and +1. So what -1 and +1 is representing? If we see the +1 means the two bands increases together perfectly. This is what +1 means in the standardized of correlation matrix. -1 means they are increases while other decreases. So they are going in the opposite direction, mean they are unrelated. In the positive ones means the bands increases together. It means they are carrying a certain information across the multiple bands and they are increasing a certain way, but with a little bit variance. Zero helps no linear relationship. There is no relationship. It is like two different things. In the negative one, it was increasing. The other one was also increasing, but if you see the negative one bands is increase while the other it decrease. So they are having a two different directions. The zero means in the correlation matrix, there is no relationship between the two classes or two pixel values. So this helps identify redundant bands. can have redundant bands in the multiple spectrals or the hyperspectrals, or even if you are going to ultraspectrals, which the bands of the difference of a nano, of 1 nano or 2 nano or micrometers. So it is really high chances that we can have the redundant bands. For example, two visible bands may be highly correlated. So highly correlated meaning they carry similar information. So holding a similar information can vast or destroy our storage even if you do the compressions already. Let's go to the next topic in the multivariate analysis. It is really important. Uncorrelated k-dimensional models. As from the word is pretty clear that the uncorrelated k-dimensional models mean if a bands are uncorrelated. We discuss in that one, zero means no linear relationship. So each bands contributes independent information, and in this case, the covariance matrix becomes a diagonal. Exactly, the correlation matrix or the covariance matrix is becoming diagonal because the diagonal informations are the one which carries a variance. It is different from the another band. In the off diagonal, we already discussed, they becomes zero in this case. And why it becomes zero? Because the off diagonals are having a little bit variance with each other, not too much, and it's not totally uncorrelated. In the uncorrelated k-dimensional cases, it becomes zero because we are looking into the spatial case to find the bands which doesn't have any differences, which has a totally different, sorry. But in real multispectral data, many bands are correlated. This is the reality, as I said, because there is a high chances because of the such short bands taken or multiple wavelength. So there is a high chances we can have the correlated because the neighboring wavelength often respond similarity, and this is there are high chances in the remote sensing applications. So when we are looking into the covariance matrix, so the off diagonal will have certain values which represents the that there is some variance but not that much. In case we can see, it will be most probably negative one. Why? Because if the one is increasing, maybe the other is decreasing, and zero means no linear. This is very rare, but also a chances high chances for the covariance matrix, sorry, for one, because that is having in a high chances. Like in multiple bands consistently, we can have a positive one correlationship because they are increasing togetherly with minor difference. Where we are having a difference of a negative covariance matrix, where let's suppose comparing the first band with the 100 band. So definitely there is a huge wavelength difference. So there is a chances of one is increasing and the other is decreasing accordingly. But real chance of a no linear relationship. So this is exactly uncorrelated data is discussing. Principal components. This is one of the core multivariate analysis. We are focusing on this and why it's important. As we have seen that in the covariance matrix or uncorrelated k-dimensional models, so we can have the relationship between the bands, or we can have a similar or redundant information. So how we should carry with the principal component transform or the principal component analysis. So principal components are a new transform bands. So this is exactly transforming the current bands, and that's why we also call them PCT or principal component transforms, or PC, a principal component analysis, in the multivariate analysis or multi-band analysis. Principal components are new transform bands created from one the original bands. They are designed to be uncorrelated with each other. There is no relationship, like it is a zero linear relationship, or the off diagonal is totally zero. The on diagonal matrix is exactly uh, representing the variance of the multiple bands. So it is useful for reducing the redundancy, useful for concentrating the certain information. And why do we need two principal components in multispectral or hyperspectral, or if you go to ultraspectral, many bands are correlated, and this create the repeated information which can disturb our storage system. So here we can have the more explanation of this same concept, like the principal component analysis. I told you already, or PCA, or we can also call them PCT, transforms the original correlated bands into the new uncorrelated components, or you can call them uncorrelated K dimensional models, because this is totally different from each other. Simple example, suppose we have a four bands, blue, green, red, near infrared. Instead of analyzing all four bands, original bands separable separately, so PCA creates new components, PC1, PC2, PC3, PC4. So it's a totally differently, but it's more mathematically combination, not a physical. So these are not physical bands. As I said, they are more mathematical combination of the original bands. So this is exactly what we are doing in the principal component analysis. For example, what PC1, PC2, PC3 represents, although we can see separately in normal way. So the idea is like PC1 usually contains the largest amount of overall variation on the data. The PC1, like the blue band, for example, in this case, they are having a very high different information or with a high variation in data. But on the other hand, PC2 contains the next largest independent variation after the PC1. And the same it is going on like in this way. So that's why principal component analysis is really important. And based on this principal component analysis, we can compare the components and look into the data. If either there is a correlation or it is redundant, so we are removing them. What is the uses of the principal components? Okay, later components usually contain less information as we discussed, like PC1, PC2, PC3. So PC4 will have more or less variation in data or the pixel values or the bands as compared to the PC1. So they may include the smaller details, classic specific variation in noise, in minor spectral differences. These are the possibilities. So PCA is useful because it can reduce dimensionality. As we said, we in the multiple spectral or hyperspectral, we have multiple bands, they are having the similar information. That was just an example. Let's suppose in the 100 bands, so we can have like 10, 15 bands of similar information. So if we make them a one component, so it really makes sense because we are removing redundancy and compressing the data and improving the visualization and support the classification as we are preparing the data for the further analysis. So principal component analysis will really help us to visualize the data and compress the data and explicitly show what we are looking for. So separate important features or patterns from the noise and transform correlated bands into the independent components. That is important because if you're looking to consistent bands, it's running like this way. So if we are having a multiple bands in similar information, so multiple losses like time usage, we are looking into the every bands and with certain difference or little bit difference or redundant information. So this is the best in cases that the principal component analysis making them the independent component. So when we are looking to a certain components, we are looking into totally different information. That's important. The original bands versus the components. This is a short comparisons as I said, this is the mathematical representation. It's not a physical exactly. So there is a misconception that where the original bands going on in the principal components. So in this case, if we see the original bands are the physical spectral bands or hyperspectral bands, multiple spectral bands. But the principal components are the mathematical information bands. But in the original bands may be correlated because there is a chances of a correlation. We said there is a narrow bands between or narrow bandwidth between the two different bands like of a micrometers or 2 micrometers or nanomicrometers even in the ultra spectral. So in the principal components, they are not correlated because they're removing redundancy, noise, and they are looking for the patterns as we have discussed in the previous slide. They are separate the important patterns from a noise and transform the correlated bands into the independent correlated uncorrelated bands. based on a sensor wavelength. Exactly, the original bands have been taken on based on the wavelengths, multiple wavelengths, but in the principal components, it's based on the variance or information we are having in it. In the original bands can contain the redundancy, but in the original there is no redundancy. And even in the principal components, we can have a less noise also if we remove the certain unrelated noise information from that bands. If we are capturing in one and the other, and if we compare both of them and there is a noise, if we subtract them based on the math operations we discussed in the basic tools in the previous lectures of the data correction and basic tools, so exactly there is a chances, not chances, but it's obvious, we already discussed. If we see the remove redundancy, dimensionality, compress information, and professionalization support classification, separate important patterns from noise. See, we are removing the pattern or separating the pattern from the noise. So automatically in the principal component, the noise has been already gone, but there is available. So that's why the principal components analysis is important and it comes into the picture. In short words, this is the easy explanation or summarization of, you can say, of the principal component analysis or principal component transforms. Principal components are a new images layers obtained by transforming the original correlated spectral bands into a new set of uncorrelated components. In short, the first component contains the highest variance or information. The second contains the next highest independent information and so on. This helps reduce the redundancy and concentrate useful information for the analysis. This comparisons is really important. Like where the physical bands, spectral band, here is mathematical, and this is a really related and it's uncorrelated. It is based on the sensor wavelength, it is based on the information, and they can have redundancy, but they cannot have a redundancy. This was also short summary. And this is the overall lecture 7 exact extra information, you can call them. For the remote sensing data analysis, we have covered the pixel values distribution. It was exactly a summary of the core ideas we have covered. That's why it's really important. We have covered many things: pixel value distribution, like histogram, spatial relationship among the neighboring pixel, spatial analysis, multi-bands relationship among the spectral bands. We discussed this multivariate bands or multivariate analysis. The strongest concepts are the histogram and models. Like we have seen multiple, but these are the strongest, which can really help in terms of the analysis for the scalar analysis, for the spatial analysis, for multivariate analysis. Histogram in models for in modes for the scalar data, Gaussian modeling for the in statistics, spatial continuity in semivarograms are really important. In the semivarograms, range, cell, and negative we discussed. In GLCM and textures are the application of co-occurrence of matrix in the spatial analysis again. And kriging is also for the missing values in the spatial analysis again. Multivariate analysis and covariance we discussed. This is also really core core topics. But in the multivariate analysis, principal component analysis for redundancy and concentrating information, that's really important. If you look into the multivariate analysis and covariance we discussed here, it was more or less the same like the concept of the co-occurrence in the spatial analysis. Here we're gonna see the correlation matrix is the practical or standardized method, and this is the co-occurrence matrix, covariance matrix. So they are describing how bands vary together. I mean, or how one band is vary from another, which band is increasing, how it is, which one is decreasing, and how it is independent and similar information. In the standardized method, we have seen like with a positive one, negative one, and zero. So this is also really important. So this was a short summary of the whole lecture. We have seen so far all the ideas and topics we have discussed. So the next lecture will be a new glance. It is about the advanced analysis and its application. And it will be the second last lecture. And we will see soon in the next lecture. For now, bye. See you.